This is our setup for observing electron diffraction. We use a vacuum tube and a high voltage power supply. I'll hold the vacuum tube up so you can see it. You can see the different parts inside here. There's an electron gun back here that shoots a beam of electrons through a graphite foil held by this frame right here. If I turn it toward the camera, you might be able to see the foil. It's the slightly different colored tiny circle at the center of that front disc. So the electrons are diffracted by the graphite foil, which acts sort of like a microscopic diffraction grating. Then they fly through the vacuum tube. Because these are low energy electrons, they would get stopped by air, so we need to have all the air pumped out of the tube. And as the beam flies from here to here, it spreads out, just like any diffraction pattern, gets bigger so that we can more easily measure it. And on the front, we have a phosphor coating, which is similar to any old-fashioned CRT tube like on an old television. On the high voltage supply, I've got the high voltage turned down all the way on the knob, which is good practice before you turn on a high voltage power supply. You can see I've got a whole bunch of complicated connections here. Most of that complication is just because it's hard to produce a nice thin parallel pencil beam with an electron gun like this. So they have lots of complicated electrodes that kind of shape the beam and focus it. Also, when I turn this on, it's got 0 high voltage. However, the back of the power supply has a connection, which you can't see, which is just a low voltage connection that turns on this heater back here. So that's what some of those other connections are for. Without the heater, not enough electrons come popping out of the cathode in order to make a visible beam. So the heater heats up the metal. The electrons start moving around faster because heat is the random motion of atoms and molecules and electrons. And then some of them are moving fast enough that they spontaneously jump out of the surface of the metal and then can get accelerated. This thing's designed to work with about 5,000 volts. So I'm going to turn it up to 5,000 volts. And the web camera is not doing a very good job of adjusting the brightness, so you can't really see the diffraction pattern. So now I'm going to switch to still photographs so that I can control better the brightness and contrast. Now I've switched from the webcam to a manual control camera that allows me to control the exposure. The webcam tries to figure out how bright to make things, and basically it guesses wrong. So I think you saw before that it made the diffraction pattern so bright and washed out that you couldn't see anything. Now that I've manually reduced the exposure a lot, you can see that there are really 3 features on here. There's a very bright central dot. That's the m equals 0 maximum of the diffraction pattern. And then you have the 2 rings, each of which is m equals 1. So on a normal diffraction grating, we would only have a single m equals 1 feature because there's only a single dimension of the diffraction grating, the spacing of the grating d. Here for this graphite crystal, we really have 2 Ds, which are given in the lab manual, and that's why we get 2 different m equals 1 rings. And the reason they're rings rather than dots like you would get from a diffraction grating is that the graphite crystal is actually made out of many small crystals, each of which is randomly oriented. So what we're seeing is the diffraction pattern smeared out and averaged over all those orientations, so it makes rings. We use the voltage to control how fast the electron beam goes. It also has the side effect of changing the brightness of the pattern. I have the voltage pretty high right now. I have it on 4 kilovolts. That's somewhere in the range where the tube is designed to be used. It makes a nice bright diffraction pattern that's easy to see even with the lights in the room on. However, we're trying to study how the wavelength of the electrons depends on their energy or momentum. That means we need to have data over a range of voltages, and to get a good range we need to go down to some very low voltages that are considerably lower than the tube was designed to be used with. So at those low voltages you'll see that it's very, very dim, and so what I'm going to do is I'm going to turn off the lights in the room completely, and then I'm going to show you a series of these still images with the lights off, and you'll be able to see the diffraction pattern as well as possible. You can go ahead and take measurements off of the screen of each of these, either using a ruler, or if you have software that allows you to measure distances on the screen, that works too. I think as long as you maximize the window so it fills your full screen, you'll get about as good precision as you're likely to get from this. The main limitation is that the rings are simply fuzzy. You can either measure the diameter of the ring, which means you're measuring from the fuzzy ring to the fuzzy ring on the opposite side, or you can measure from the central dot to the ring, which means you're measuring the radius. I find that easier because I think the dot is so well defined and easy to see. It makes that error associated with locating the dot negligible. Here's 5 kilovolts, which is the highest voltage the power supply can create. By the way, this is the brightest pattern and the easiest to see of all of them, and you might think maybe we could see the m equals 2. There should be 2 more rings farther out in angle, roughly twice the angle. However, I can't see those, so they're either too dim to see or they're not falling on the phosphor. You can go ahead and pause the video and take your measurements for this voltage at your leisure. Here's 4.5 kilovolts, and now for the first time you should be able to tell the trend of the data. That would rule out some of the possibilities that were proposed in the lab manual for the dependence on the wavelength on the speed of the electrons. I think you can also see pretty clearly in this shot that the inner m equals 1 ring really is a ring with some dark space on the inside of it. It sort of looks like it's filled in, but it's not theoretically supposed to be like that. That filled in stuff is probably just poor focusing of the beam spilling out from that m equals 0 central dot. So, and by the way, you should be measuring both rings in all of these. It's a good idea to have both measurements. It gives you a visual check on your graph of how much random error there is in each of these measurements. 4 kilovolts. 3.5 kilovolts. Now I think you can see that the pattern is noticeably dimmer. 3 kilovolts. Now we're at 2.2 kilovolts, which is way below the lowest voltage the tube is designed to operate at. At this voltage, I can just barely see the inner m equals 1 ring and get data. The outer one is too dim for me to see, and this is about the lowest data point we're going to get. You can also see that the central spot is a little bit rectangular at this voltage. I'm not sure why, but basically the beam focusing is probably not designed to do anything sensible at this low voltage. So even though you only have 1 ring, you can still get data here that tells you what the wavelength of these electrons is. I thought I would try to go a little lower and see if I could get any data at all. This is 1.9 kilovolts. All I can really see in this image is the m equals 0. I can't really see anything but maybe a tiny hint of the m equals 1. However, I then played around with the image a little bit in a photo manipulation program. It's called GIMP. It's the open source equivalent of Photoshop, and I was able to get that bright enough so that we actually could see it. So that'll be the next shot. So here's that exact same photo, but just with the brightness and contrast jacked up a lot, And surprisingly, I was able to get so I could see not only the m equals 1, but now again the m equals 2 at this very low voltage. Here's where to find the lab manual that describes this lab in more detail, including all the theory. It gives the numbers for the spacing of the graphite crystal. And by the way, nowhere in this video do I bother even measuring the dimensions of the tube. That actually doesn't prevent you from doing the analysis. If you use small angle approximations aggressively here, you actually don't need to know the length of the tube at all. And in fact, you should throw out all constant factors because they just complicate your life without giving you any benefit at all.